Welcome to the 5th edition of the workshop on Planetary-Scale Distributed Systems. I'm João Leitão, I'm one of the organizers of the workshop. The other organizer is Bernardo Ferreira, who's here. So before we go for the first keynote, let me just give you a bit of context. So this workshop is operating in a different way than in previous editions. The workshop this year has the scientific sponsorship of the Lyon European project, and so many of the talks are keynotes from people involved in the project. We decided to keep the workshop open to outside contributions, and we do have one accepted contribution that will be presented later on. And basically that's it. So Peter is the coordinator of the Lyon European project, Peter Van Rooij. He's a full professor at UCL in Belgium. He's going to talk to us about some reflections on scalability and consistency, which I hope will be a very interesting topic, as usual, from Peter. And that's it. So,
okay.
Thank you.
So, thank you, João. So, I'm going to give a talk which is not really a usual technical talk. It's more like a collection of things that I, after many years, kind of found out about scalability and consistency. So it's basically a kind of a fun talk. There's still some technical parts, but it's fun, and it's supposed to trigger your imagination. So I'm going to start by saying a little bit about what is scalability, why do we need it, because the internet is still growing exponentially, so the growth has now moved to the edge, Internet of Things. I will refresh your memory on the CAP theorem. Then I'll talk about some large-scale phenomena that appear when you start building large-scale systems that are kind of weird. There's Buridan's principle. This is actually a Lamport article from 1984. If you don't know, you must read. I'll talk about black swans, real-world graphs, and a new kind of application called Heisenberg applications. And then I'll talk about some ideas of how to build scalable systems, a little bit about autonomic computing, but this leads to a more elaborate approach called feedback structures. I'll also talk about convergent data management. So there's basically two approaches here, control-oriented and data-oriented approach for management. And also some kind of novel, interesting approaches where you assume kind of a simplified distributed system and you add the general bits, a small amount, but the general system is very simple and easy. So this is a kind of an interesting new approach, and I'll show two examples of this with confluence and linearity. And that's basically it, and then I conclude. So we're working on some of these. Some of these are things that I've collected. So scalability, so it maintains a desirable property as the scale increases. I'm not going to be very precise on what scale means. There's different ways to define it. Number of nodes, size of data, number of users, how geographically separated it is. Basically, we will roughly look at the total aggregate work, computation data being done by a system. So when the scale increases, unusual things happen. So this is kind of the fun part, things that are unexpected. So this is really not kind of a standard technical talk, although I will show technical things. I'll show some various phenomena that show up and some approaches to address it. So if you're really serious about scalability, this is stuff you have to know, even if you don't encounter it every day. You may encounter it. So I'm trying to provoke discussion, and if you have other interesting phenomena in your experience, I would be very happy to hear about them. Okay, so the scale. So scalability is still an interesting subject. So the internet has been growing exponentially since around 1970 when it started, and it still is. And the growth is now happening at the edge. So this is a slide I took from a talk of David Bolt, who actually is giving a very nice talk on sustainable energy in terms of ICT. He's giving it in Paris, actually, this week also. So this is a second order extract, because David Bolt took this slide from ARM and SoftBank paper. So you see the number of cumulative devices. This is the devices, IoT devices added per year. These are billions, so 1 trillion cumulative by the end of the 2020s. And then a very nice statement from Thomas Wittmann, the Gartner block network: the edge will eat the cloud. It's coming and it's going to be big. So the scale, the exponential growth is still going on. All the pointers are going it, but it's the edge. So the age, the cloud age is over, and the edge age is arrived. Okay? So just I'm now going to refresh your memory on a very important result called the Cat theorem. I hope all of you know about this. So this was conjectured in 2000, proved in 2002. So there are three properties that you cannot obtain simultaneously. So consistency, availability, and partition tolerance. Consistency in your distributed system means that there is a total order among all operations, and all operations are atomic in the system. Availability, every request eventually returns a result. And partition tolerance, messages may be lost. So this, you can have any two. You cannot have three. This applies always for all systems, at all levels of abstractions, all sizes. So this is a very important tool when you start looking at scalability. But it's only the first step, as you will see. So you can actually arrange this in kind of a triangle, the Cat theorem. So each corner I have two of the three things, A plus P, C plus A, C plus P. But if I want all three of them, so I can actually make a spectrum, where here I'm getting a little bit less P and more C, for example. And then I actually add another dimension where toward the center you pay. The cost increases. So if you're willing to pay a huge amount of money to make an incredibly redundant, reliable network, only the best stuff, Google for example, then you get closer to the center, and you can almost cheat the Cat theorem, because maybe you will never have partitions, for example. So basically, this is a kind of a navigation. And if you want to build a system, you're always going to be in there somewhere. Okay? So that's just refreshing your memory. Now let me start talking about some interesting stuff. So the first one is Buridan's principle. Some of you probably heard of it already. So who knows this already? No. You know it. Well, great. Then I'm very happy to have chosen it, because it's a really amazing thing. So this is a medieval philosopher, Jean Buridan, scholastic. He stated that an ass, a donkey, placed equidistant between two bales of hay, must starve to death. There's no reason to choose one over the other. Now, this principle seems kind of dumb, you know, why doesn't the ass just go for one? But actually it has amazing consequences, and this is in a paper called Buridan's Principle, by a young Leslie Lamport in 1984, which I strongly recommend you download immediately and read it, okay? But I will give you the important ideas here. So the idea is the following. Assume you have a system, any system, it has to make a discrete decision from continuous input. So for example, student has a score from 0 to 100%. The discrete decision is, does he pass? Okay? Then we can prove the following theorem, and I will pretty much prove it for you in a minute. A discrete decision based on an input with a continuous range of values cannot be made within a bounded length of time. That means there are values of the input for which the decision will take arbitrarily long. That seems very weird, huh? But it's very, very profound principle. So there are many examples, and actually Lamport gives many. So a car at a railroad crossing on the street. Do you stop? The train might be coming or not. Do you stop, wait for the train, or do you cross? You have to decide. It's a discrete decision, cross or not. The train is coming. You don't know when. It's continuous variable. There are situations where the car actually, where it's extremely dangerous, because the car will take arbitrarily long to decide. So the idea is the following, eh? So the car is trying to decide. So he sees the train coming, okay? Then he says, I want to stay. But maybe he can cross, okay? But as it gets closer to the boundary, it gets harder to figure out whether it's safe or not, okay? And there's no way to get around that. Some of you may already also know the second one, a student, pass or fail. So it has a bunch of scores, a bunch of information about this student. as the student gets closer to the threshold, it gets harder to decide. You know that in these juries you spend most of the time on the hard cases, right? That's an example of Buridan's. Okay. So, why is this true? Well, let me show you a proof of this. So here is a function, a0x. It's a position at time t with a starting position x. So I start here, okay, and then I end up here. Okay, I'm starting from 0 to 1. Now I'm ending up from 0 to 1. So at time 0, I have not moved yet, so it's just a line, okay, like here. So I start here, and I end up at the same place. But after 1 second, I've started to make a decision. Okay, and if I start here, maybe I end up here. Maybe the decision will be 1, maybe it will be 0. So as t increases, more and more of the values of this function will be either 0 or 1. Now, the critical point is, this is a continuous function. It's continuous in x and t. Okay? That means what's going to happen is it's going to get more and more and more and more vertical as t increases, because we're going to be more and more and more deciding. But at some point, it has to jump from 0 to 1, because it's continuous. Okay? And this jump is not an instantaneous jump. It has to move up from 0 to 1 for every value of t. And all the values on this line are values for which we have not decided yet. So as t goes to infinity, this line will always exist, which means that there will always be values of the input for which we have not decided, for any value of t. Okay? It's interesting, yeah? So it's very profound. So let me make now the connection to scalability. Distributed systems often have to make decisions. So one example we used a lot in life code is distributed bank accounts. Okay? Is your value of your account positive or negative? Or a voting system. Who wins? Distributed voting system. So the input data is continuous, or approximately continuous. And for performance reasons, we like to distribute it over the whole system. And we need to make a decision. Okay? But if we get closer to the boundary, like maybe my account is very close to 0. If my account has a 10 million euros in it, I don't have to worry, and pretty much always it's going to be positive. But if my account is getting close to 0, the decision gets harder. Okay? I need to collect information from all the nodes that know something. Maybe I've distributed my account information. Maybe I've used escrow, where somebody has some knowledge, has reserved some of my money, so they can locally make transfers. Well, as it gets closer to 0, I have to know that. Okay? So when you get very close to the boundary, actually the whole system will be involved in the decision. So it gets slower. So this is a lesson for system design. Don't go close to boundaries. Boundaries make your system slow. Of course, you can't get around boundaries in many cases. Voting system, you have to know who wins eventually. So then the idea is, maybe you want to try to do some prediction and prefetch information. But the notion is that the boundary is a very interesting and critical place where things slow down. And this is a consequence, when you think about it, of Buridan's principle. Okay? So that's a first insight in relation to scalability. Let me now give a second insight. Also a weird thing that happens. Black swans. So maybe you have read the book Black Swan by Nicholas Nassim Taleb. So this is a basic idea of what is a black swan. But I have to give you a quote first from Goethe. You know Goethe? Goethe, the famous German poet and scientist, and did many things. So there's a very interesting book called Conversations of Goethe with Johann Peter Eckermann, which was from the 19th century, but I'm quoting from a 1930 English translation. A very interesting book, by the way. Here's a quote. Imagine a green plant shooting up from its root, thrusting forth strong green leaves from the sides of its sturdy stem, and at last terminating in a flower. The flower is unexpected and startling, but come it must. Nay, the whole foliage has existed only for for the sake of that flower and would be worthless without it. So what it means, you see this plant growing, leaves, it's getting more and more leaves are coming. So you think, oh, it's going to be growing and leaves coming. And then something unexpected happens at the end, flower, okay? So this is a black swan. So when we design systems, we rely on induction, in the sense of reasoning, what happened in the past will happen in the future. And it is very common to assume that induction works. But it very often has a built-in limit and will fail beyond. Sometimes it's even predictable. I remember, many of you don't now, but I remember very well the year 2000 bug. It was a big, big thing in the 1990s. Ooh, we had COBOL programs with 2 digits for the year, and in the year 2000 the world was going to end. Okay, all programs were going to crash. But this is an example. But this one was predictable. Also, dinosaurs 65 million years ago. Banks, there was a problem with banks some years ago. If you look at some decades ago, another problem. Too big to fail, right? They haven't failed in the past, but they will fail. Okay. This is ubiquitous in computer systems. All computer systems have finite resource limits, of course. Memory speed, and a lot of work is done to hide these limits, and in normal usage we are far away from them, okay? And it will, typically the system will fail in exactly the case where it's needed most. And in fact systems will be accumulating errors, or there will be small memory leaks or something, and so the failure is certain, okay? So there's actually 2 great frauds in system design. One of them is actually mentioned by Nassim Nicholas Taleb, who wrote the book The Black Swan, another very good thing to look at. Systems obey inductive reasoning. False. Past experience is a bad guide for future, especially if the future system is going to do something that the past system is not doing, okay? Also, systems obey probability distributions. This is a huge thing that people will always assume to simplify analysis. But there's no reason to believe that they exist in reality. So a probability distribution is actually an extremely strong assumption. It means that a limit exists of frequency as the number of events goes to infinity. That's an extremely strong assumption, and very often limits don't exist. Maybe it just keeps oscillating or whatever. So assuming it exists is very strong and is very probably wrong. But it's the only way to do very simple analysis. So these 2 are where we impose our way of thinking on the system. But the system doesn't care about that, okay? So a black swan is an unexpected large event that falsifies induction, but actually it's obvious in hindsight, okay? So large systems fundamentally have this, and they have to be designed to survive such extreme cases. So in fact, if you build large systems, you will see different degrees of irregularity. So the first one is the most tame kind of system, very tame, very easy. Existence of a probability distribution, statistical physics holds. You can actually use thermodynamics for these systems. It's so nice. And most simulations, they get stuck here in analysis. And then once you get to the limit, okay, you actually see critical points arriving. So a critical point is a point where small fluctuations get amplified. Small event can have huge consequences. So computing systems often have these points. So usually we don't like them. So people, when they run their systems, they stay in this very nice place. They never push to the limit. So garbage collectors, for example, or virtual memory, if the working set size starts to approach the size of the RAM, small things can have big effects. So we start getting into a critical point. Same for garbage collectors. If the active memory size starts approaching the RAM size, problems. Okay? And then the third level is no probability distribution exists. All we know is the range of behavior. The limits of frequency do not exist. Actually, a very famous computer scientist, whom you may have heard of, I hope, Edgar Dijkstra, who was a big guy in the beginning of computer science, he understood this, there's a thing called the guarded command that he invented, where you have a bunch of conditionals, and each one has a Boolean condition, and you pick one that's true. So there's no probability distribution here. All guards with that are true can be chosen. So the program must be designed to work, even if a daemon makes the worst possible choices in each guard command. So this is come to be known as Dijkstra's daemon. So just as electricity has their own daemon called Maxwell's daemon, we have also a daemon called Dijkstra's daemon. You must listen to this guy, okay, or your systems will crash. Okay, so that's black swans. What do you think of that? Nice? I go on, more interesting stuff, real world graphs. Now we're looking at sociology, now we're looking at social networks. So large applications on the internet, they will often have large numbers of users, millions of users maybe, huh? Or if you're not that successful, 100,000 users, still a lot. So the behavior of these users will influence the behavior of the system. So what's especially important is how these users exchange information. And there's some very interesting laws here that it's very important to know when you build large systems, okay? And two concepts, very important concepts. The first one is called a small world graph. You all know what that is, right? So who knows what a small world graph is? Ah, okay, some people, half. That's not bad. It's more than Buridan. So a small world graph is a graph with a special kind of a property. So a small world graph is not a random graph, but it's not a nearest neighbor graph either. Okay? The shortest path length, the average shortest path length is small. That means all nodes are close together. So even if you have millions of nodes, there's short links, but there's also faraway links. So you can always get where you are, get where you want to go with a small number of hops. So that's a nice property. And the clustering coefficient, on the other hand, is large. So it's very clumpy together. So it's more clustered than a random graph, which is like uniform. And it has smaller paths than a nearest neighbor graph. Nearest neighbor graph, you have to do long routing. So actually, navigation is often easy on such graphs using semantics, using user information. So if you have a system with a large graph like this, if you're smart, you can actually navigate pretty nicely on such a graph. So this was proved using some experiments. The famous 6 degrees of separation experiment by Stanley Milgram, where you can send basically a letter to anyone in the world by forwarding it to somebody you know who you think is closer to the destination, and it will arrive. So the median, or the mode, sorry, is actually 6 degrees of freedom. So a very, very small number of hops. So this specific form of graph is, you find it always when you have real world graphs coming from the real world. They will always be like this. And such graphs are related to another important property called the power law structure. So for example, look at the web. The fraction of web pages with a certain number k of inlinks, so pages pointing to them. So the fraction of these among all the web pages is proportional to 1 over k squared. Pretty close to 2. It's actually slightly more than 2, 2.1 or something. So it's a power law. So basically, there's a long tail. So the pages that have more and more inlinks, okay, are less and less frequent. Okay, the more popular pages are less frequent. But it's not an exponential. It's not Gaussian at all. It's power law, which means as k grows, it goes down very slowly. Very slowly, okay? So assuming Gaussians among these real-world graphs is wrong. Never assume Gaussian. Gaussian has this exponential to 0. It's completely wrong. It's a power law structure. So I highly recommend this book called Networks, Crowds, and Markets. So, which explains a lot of this. You can say more. So what about consistency in such real-world graphs? So a big social network graph. Okay, so we have the cap theorem to fall back on. Consistency cannot be achieved for available partition-tolerant systems, but actually we can say more in a real-world graph because of how the users disseminate information. There are certain properties that are recognized, and I give them the official names here in red. So there's a property called pluralistic ignorance. Different parts of the network will have very different information. And this is kind of a metastable state. Huh? They will maybe believe contradictory things. But this is not going to change. It can last very, very long. And it's a consequence of the fact that communication is actually limited. So they're not actually partitions, but this is kind of a self-sustaining thing. These communications are limited, and so this pluralistic ignorance will be maintained. Inconsistent information in different parts of the system. So if you build a system, be careful about that. Of course, we're seeing a huge example of that right now, an experiment in the United States where it's extremely polarized. That's only one example. Huh? In every social network, there will be groups with different information. Also, limiting the communication can cause very sudden changes, like basically collapses or discrete, immediate, very, very fast things, sudden things. So for example, one example is epidemic dissemination. This is kind of intuitive. If I bring new information into the graph, it will disseminate and it will propagate. Usually this is very fast, but strange things can happen in some cases. There can sometimes be oscillation, or information could die out. Certain kinds of information are temporary. Maybe it's information on something like football scores, and then after a certain while nobody's interested anymore, so they forget it. But that means you have kind of waves of information going through the system. So you have this issues of the system behaving in a synchronized way because of this, pulsing it, also oscillating. Sometimes it's stable. But depending on the form of information, this is going to be different. Actually, the mathematics of this is very similar to disease, epidemics. A second sudden change is called a collapse of a giant component. So every large network, a real-world network, has, most of the time, a single component that is connected and that contains a significant fraction of all nodes. So, for example, if you take the network of people who know each other, there's a link between people if they know each other. And if you look at all people in the world, for example, then the number of people who don't have a path to one of us is very, very small. Maybe somebody who's grown up in a small village somewhere in the suburbs of Samarkand or whoever knows, and they don't have any connection. But the number of such people is very small. And most of the people in the 7 billion people in the world will be part of a single giant component. So that's a stable situation. But if you have two pieces of the system that were partitioned, they will have separate giant components. And when the partition goes away, there will be a sudden collapse as the two giant components merge. And the famous example of this is the diseases between Europe and America. South America, to be precise. So, before the explorers visited South America around the 15th, 16th centuries, these populations had no connection to each other, so there were two giant components. And assuming the component is disease, microbes, propagation, as soon as there were explorers coming in, it made a connection between Europe and America, and all the disease microbes from Europe went to America, so the giant component collapsed. There was only a single. So there were two before, and after there was only one. So it's kind of like the merging of two black holes. That's kind of a really violent event. And what happened in this case was people were dying all over the place in South America. There was many, many epidemics. It was really, really a catastrophe because of the giant component collapse. Okay, so there can be sudden changes. So that's, as a systems designer, you have to realize there can be sudden changes when you build a big system. Also, Also, a third thing here is that while your system is running, information can change. You might think it's stable, but it's not. So you have there's two examples here. One is called cascades. A cascade is when a decision is making in sequential order. So I have to decide which thing to buy, and I'm the first person, so I kind of decide randomly. I buy brand A. And then a second person wants to decide, looks at me, says, oh, he bought brand A, maybe brand A is better. So he has a tendency to buy brand A instead of brand B. So if the decisions then are made sequentially, what happens is that the early decisions tend to dominate. But it's not that stable. It can change. There can be sudden changes in this, okay, where a certain number of people will tend to buy brand A in the beginning, but somehow there's a fluctuation, and then it flips to brand B for the rest, okay? So it gets rarer when the number gets higher, but it doesn't ever completely go away. So you have this cascading or herding effect if you have decisions made in sequential order in your system. Okay, a second effect is called tipping points. This is, let's say you bring a new product on the market, a fax machine, okay, it's highly, I'm giving you a tip, you know, you make a lot of money building fax machines. So, but in order to work, a large number of people have to own one, otherwise it's not worth it. So there's a tipping point. You need to convince a large initial group to buy the system, and the system then will flip from one state to the other. It'll flip from a state where nobody has it to everyone has it. So all companies bringing in products that depend on this network effect are trying to game the system here. So if you're in one of those internet thingies, areas where there's lots of people connected, and people are trying to bring out new products, everyone is going to try to tip their product, okay? So this causes some interesting kinds of fluctuations in the system, so you have to be aware of that, okay? And let me now just give two more examples of such huge real-world graphs. So the web, the World Wide Web, has been built in a completely decentralized way. People add web pages, they word of mouth, whatever, they get information, they put links on their pages. So it's completely decentralized and kind of disordered. But despite that, the overall web has a very simple global structure. So this diagram is from the year 2000, so the numbers are kind of out of date. But it's still true, only the numbers are higher today. So you have a strongly connected component in the middle. This is the biggest one, 56 million nodes. So it means there's a path between any two nodes here. Then you have nodes coming in, where they go into the strongly connected component but not out. And then you have, from this strongly connected component going out, so these are a little bit smaller, but they're the same size. And then you have weird things like what's called tendrils. So from these in nodes, you can have nodes, links that go nowhere. That go a while, go nowhere. Or you can have nodes from the in that go directly to the out without bypassing this strongly connected component. So these are called tubes and tendrils. And you have a small number of totally disconnected little webs, okay? But the main web is this. There's a central, strongly connected component, okay? So if you didn't know about this, it's important to know that the web has this kind of a structure, a global structure. And if you build an information network where it's built in a decentralized way, and people will be adding information and connecting information, you can be pretty sure of some kind of a structure like this will appear. Okay? So here's a second example, another one with this strongly connected components. So this is the network of loans among US financial institutions. So there's a link between two nodes. The nodes are like banks or institutions that lend money. There's a link between one if they have lent money to the other. So if I lend you $1 billion, then there's a link between me and you, okay? And you have this billion, and so you can lend money to other people and so on. And then I actually have given away $1 billion, so I'm poor now, so I have to borrow money. So this makes like cycles and so on. Huh? So the center of this network is a strongly connected component, this whole core is strongly connected. That's actually very dangerous. If one bank here defaults, it's going to bring down a lot of banks around, unless the other ones can somehow fix things, but it fragilizes a lot the system. It's because a bank that lends will also borrow. There will be lending and borrowing going on, and there's a lot of cyclic dependencies. So there's a structural fragility. So in a system like this, so real-world network, where you have these dependencies, so these are dependencies, huh? The dependencies will often be cyclic, and this fragilizes your system, okay? So this is another example of a big network effect. So if you build big systems, be careful. Okay, now I go to another thing. One more thing, but there's many more things still. So Heisenberg applications. So this is new. This is for clouds, but actually people sometimes don't realize the fundamental effect that clouds give. So many real-world applications are bursty. They require a lot of resources for short time periods, interactive applications. And you see that every day, even on your computer's CPU. It's actually pretty much bimodal. Either it's idle, pretty much idle, or it's 100%. Like, let's say you're formatting videos or something, or doing some computation, then you can use as much computation as the system gives you, 100%. So, quad core, core i7, all the cores are busy, 100%. Or it's doing nothing, like right now it's pretty much idle, this system. So bimodal. So the 100% is actually approximating infinity. So elasticity is the solution to this. So this happens in two places. So of course everybody knows cloud computing. You pay for the resources that you actually use. But also it's true, or it will become true, for Internet of Things. You power up only the nodes that you actually need. So for example, you have 1,000 core system on the edge. Most of the time it's off, unless you need a huge compute power. Maybe it's doing real-time voice translation. When you talk, all the cores power up. Okay? And it's important because power is a scarce resource on the edge. Eh? So a new kind of application based on burstiness. So the pay per use and elasticity are key properties, but you can actually quantify this with cost. So the cost is related to the product of the resources and how much time you use them. Okay? So there's actually an analogy with Heisenberg's uncertainty principle. Product of uncertainty in time and uncertainty in energy is equal to or greater than a constant. It means you can do anything you want as long as you're less than that constant. Okay? So Heisenberg's principle is actually a motor. It's like the curtain hiding God's kitchen. God can do anything he wants as long as he does it in a short enough time. If he uses high energy, it has to be a very short time. If it takes a long time, it has to be very low energy, because there's a limit in product of these uncertainties. So new applications can be done. So this is actually a fundamental change that you have to understand. So here's a time interval, and here's available resources. So the light blue part of this graph here is resources limited by a fixed number, maximum, R0. So before clouds, we were always sitting here. But if you have clouds, then you can increase the resources and shorten the time, as long as the product is less than the cost that you have to give it. So this new dark blue area of applications appears with cloud. Okay, so this is the fundamental new thing. So cloud is not just a quantitative change, it's also qualitative change. And it turns out machine learning, it's kind of a synergy effect. Machine learning all often sits here, because it will be needing a lot of resources for short time periods. Okay? So the fundamental new thing in cloud and Internet of Things, it will come. So this is my prediction. And it doesn't completely exist yet, but because hardware is cheap, this is not true only for clouds, but also for Internet of Things applications, data fusion. You have this new kind of application appear, which did not exist before. So a qualitative difference. So here's kind of a space, if you want to look at it. Actually, it's very focused on learning, which is a very important tool in this area. So there's 3 axes. You have the learning phase, where you have to learn. And then you have the inferencing phase, or the query use phase. And in both of these, you need elasticity. So here I have how much? Small elasticity, medium, large, extra large. It's very qualitative, huh? Small, medium, large, extra large. And then you have the degree of interactivity. So one shot, you just need one result, a one-way stream. So information is flowing out. So for example, Google search is like that. I make a query of a database, but there's no two-way conversation. See, Google will be scraping information, but between me and the system, there will be no two-way conversation. So the third level is an actual conversation. So this is typically something like a chess game, or something where you have to do thinking depending on the input and in both directions. Okay. So here is some kind of a geography of this space where you see where these applications sit. So you have these IPM Jeopardy, you've heard of, championship chess programs. Weather forecasting is here. You need a lot of power to predict. It has to be very elastic because you want to do the prediction very fast. But the querying is not so big deal, okay? Whereas in something like a chess program, that the chess program exists, doesn't have to do anything anymore, but each time you want it to calculate a game, it has to do a lot of work. And then you come up to this very future area, real-time language translation, real-time expert guidance, creative problem solving. I put on my goggles, my augmented reality goggles. I open the motor, the hood of my car. I see the motor. The goggle says, it imposes information. It says, here is the screw you have to unscrew. I unscrew it. Here is the cable you undo. Here's the thing you do. So I become an expert mechanic, even though I don't know anything about car mechanics. Okay? So this kind of thing needs enormous computational resources, of course. So this is a space of future applications. And you see, it's actually fundamentally built on top of elasticity. Okay? Okay, now let me go into the second part of the talk. Things, how to build scalable systems. So I've been kind of showing you phenomena that appear, building scalable systems. So every scalable design starts as independent pieces. I have a bunch of pieces, a bunch of human beings that are just wandering around randomly, but we have to organize them into a society, a nation, a country. So we have P and A, but we have no consistency because they're not talking to each other. So the way to build the system is to have interaction between nodes. And then we have this notion of a split and a merge protocol when a node leaves a group. So a group is a set of nodes that actually interact in some general sense. It could be anything. It can be a distributed database, structured over the network, Facebook, whatever. Nodes split and merge when you leave a group, when you join a group. So many things can be seen in this kind of a viewpoint. So we're going to show how to add some consistency. And I'm going to show two approaches, one which I call control-oriented approach, the other one which is called data-oriented approach. Control-oriented is actually very well known right now because it started with autonomic computing, and then it evolved from there. So I'll talk about weakly interacting feedback structures. The data-oriented approach is something we're actually doing in the project, Lyon project, is where the data structures kind of maintain and manage themselves. They have behaviors where they're actually converging towards the correct behavior, and we're actually building, we have actually a reference architecture and artifacts that use this approach. So this is an approach we're actually doing research on. So I'll explain a little bit those two approaches. So the control-oriented approach. So it starts with the Autonomic Computing Initiative, initiated by IBM in 2001. So you know IBM? IBM consists of a huge number of people wearing suits and ties and managing. Okay, they're managers. And they want to make computer systems self-managing because the managers see that managing is difficult and it gets too hard. Okay? So the basic building block is what they call the make-K feedback loop. Monitor, analyze, plan, execute, based on knowledge. So actually machine learning is part of this, even though in 2001 they didn't realize it so much, but nowadays you can see that machine learning is going to be a big part of this. So this is a single loop. But in fact, systems consist of many, many, many interacting of these loops. So how do they fit together? So this was something we did in a project called Selfman a few years ago. How do these loops, these MAPE loops, fit together? So we actually built an approach. There's 4 levels. So the system consists of concurrent components sending messages. So this is a very common way of building distributed systems. Erlang does this. There's a very interesting book on distributed systems by Luis Rodriguez and Rashid Girwi, which if you don't have, you should buy immediately, and uses this approach to define systems. A single loop here, a single MAPE loop, is a set of components, managing, sensing, and affecting, connected to a subsystem, and managing continuously. So this maintains a local goal. But we have to connect this to the specification of the system, okay? So a feedback structure is one level up. It's a set of these loops that maintains one global system property. So the system property might be connectivity, or that routing is possible, or that, or the transaction protocol. It might be, it's some global property, and this feedback structure maintains that property, and then the overall system has several of these guys, and they're kind of connected together, but weakly. So I'll show you an example of that. So here's one example. This is an example coming from Selfman, a few years old already. This is the human respiratory system. So basically, each of these blocks is a complex component. This is what happens in your bodies when you're breathing, okay? So what happens is, the normal thing that happens is, you have this breathing apparatus, your lungs, muscles. CO2 is measured in the blood. When the CO2 increases, you have this urge to breathe. You trigger the breathing reflex and you breathe. So this is the basic move, okay, CO2. Okay, fine. But what happens when you're underwater or something and there's no oxygen or whatever? Okay, what happens? So when you're drowning, okay, so you can actually control this reflex. You can, there's a conscious control loop here where you can hold your breath. Okay, so this is conscious control. So this component is a special one because it contains all of 100 billion neurons in your brain working together. So it's extremely smart. This one, all the others are very dumb. But this one stops working when the oxygen level falls too low and your brain stops working. Okay. So, for example, you're in a car, you go into the water, and water fills the car, your windows are open, you have to get out. So basically the conscious control takes over, and it stops this, because you don't want to breathe water, okay? And you plan, the conscious control, you plan life-saving actions, you leave. Unfortunately, if the O2 falls to a certain threshold, then the conscious control falls away, okay? So the whole goal of this is to maintain enough oxygen in you so that you live, okay? So this is a feedback structure maintaining a single global property, okay? Now notice there's a funny one, which maybe you've experienced. I'm eating a piece of chicken. The chicken goes into the wrong pathway, into the lungs. All of a sudden I can't breathe. I get panicky. You ever had that? No worries. This is actually completely normal. It means that your lung has detected this thing coming down and has closed the passageway. It's called a laryngeal spasm. So it temporarily blocks the breathing passageway when there's an obstruction, seals the air tube. So you cannot breathe. But it actually does not hurt this because it's on a short time span, okay? Don't worry, if you can't breathe, a few seconds later, you'll breathe again, okay? So no problems there. So you see that there is a whole series of safeties and fail-safes, and there's a complex component here that can take over when the simple components don't do their job. So this is an example of a feedback structure. But let me show now, and there's a state diagram which I won't get into. So here's an example in computing. So Scalaris was a system we built in Self-Man project. It's a self-managing key value store with transactions and built on a structured overlay network. Okay, it actually won a prize in those days, 2008, IEEE Scalability Prize, whatever. It actually consists of 6 feedback structures in the specification. So I have the key value API, I have connectivity here, I have routing, I have load balancing, I have replica management, and I have the transaction manager. So each of these S's is a part of the specification that's managed by a feedback structure. So in the structured overlay network, I have things that are failure detectors and so on that are managing the connectivity. I also have the routing tables which are managed using the chord style, these exponential fingers and so on, and replica management and so on. And there's a load balancer which depends on the routing. So these 5 feedback structures are maintaining non-functional properties of the system, and there's a dependency on them. So the routing depends on connectivity. Okay, if the connectivity falls away, then we're kind of done. If we don't have replicas, if we don't have enough replicas, we cannot do transaction anymore, but we can still route and send messages, okay, and do load balancing. So this is a system that you design with 5 of these feedback structures that are weakly interacting. Okay? So this is showing kind of how you build systems like this. Let me now talk about convergent data management, something we're doing in the Lyon project. So this is a data-oriented approach. So it's actually very complementary to autonomic computing. So we assume that our system has a database. So there's a lot of data. Many systems are data-based, based on data. So the database contains the truth, contains information that's supposed to be true. And we automate this. So typically, a lot of work is done to put information in this database to maintain the truth. So to simplify consistency management, we can automate this. We can continuously update the database automatically with information coming from the edge. And we're actually using special data structures called SRDS that are convergent, that need very little maintenance, that are very efficient, and that converge. So this is a basic data-oriented convergent data structure, conflict-free replicated data type. Maintains consistency with very weak synchronization. So as long as a replica receives updates, it's okay. So they're collecting information and they are always converging. Okay? So this is actually a very important data structure. It's actually widely used in commercial systems. It was invented by some of the partners in our project. People around Mark Shapiro, Nuno Gusa, Joao, who's here. And this has actually had millions of users. So this is actually very useful. Okay? So this is the basic data structure. So the idea is you have a huge number of edge devices, a lot of information. You have automatic information going to the database, periodic updates. And we don't care if the messages are lost, reordered, or repeated. It will always be converging. So this is kind of a data-oriented way of automating a big scale system. So we've actually elaborated this in the context of a large-scale edge computing architectures in a system called, a proposal called LIRA, Light Cone Reference Architecture. We have software artifacts. So basically we're doing what's called vertical data sharing, but also lateral data sharing on a single edge. So this is something that we're working on. Okay, so if you're interested in that, you can look at this document. And there's also an approach where you generalize this to the application invariance. So the convergent data management is always maintaining the truth. But in fact, you need more than that in an application, because your application is actually doing some work. Okay? So there's some invariance that it has. And different invariants have different consistency needs. So we want to get the best of both worlds. So this just right consistency approach will basically classify invariants according to the CAP theorem. So again, we're building on top of the CAP theorem. and we look at different kinds of invariants. So what's called AP compatible pattern or cap sensitive. So these ones, they can actually be done efficiently, but they need a test. And then some operations can only be done sequentially. Okay, so we want to make sure that the system is using the cap as good as it can. Okay, so now there's one more thing, one final thing. I have a few more minutes, but let me just maybe say one thing here. Another approach for building scalable systems is the following. So distributed systems are complicated beasts, as you know. Concurrency, latency, partial failure, real-world interaction, they're actually difficult to understand and make very nice. So one approach is to focus on a simple kind of a distributed system. So that means the simple one is very easy to build, and then making it general means just adding a few things. Okay? So let me just talk about one of them, which is one we're working on, which is called the Confluent system. So this is actually based on functional programming. So in the programming language area, you have something called the lambda calculus, which is an execution model for functional programming, but it has this amazing property called confluence or Church-Russell. Given an initial expression, the final result is the same for all orders, or reduction orders. And it turns out we can make this also for distributed systems. We place each sub-expression on its own node, and it's a very simple change in the calculus, and it's still confluent, Church-Russell. It means we have a distributed system which is confluent, which means we can move things around, we can schedule any way we want, we can send messages any way we want, and the result is the same. It's amazing, huh? But actually has a limitation, otherwise we would only use this, is that it's basically kind of deterministic. It's hard you cannot actually interact with the real world. Each agent knows where the next input's going to come from. If you have this unpredictable interaction, it doesn't work. So we need to add something, which is called interaction points. So we can build a distributed system, like here's a simple one, client server. It's completely functional except for one interaction point. This is where the server receives messages. So this whole thing is actually functional except for one interaction point. So this is a very nice approach that we're working on now. Let me go now to the conclusion. So I hope you were amused by this talk. So scalability remains an important topic. Each new scale introduces new phenomena. I showed some examples of this. I also showed some design principles. There's no silver bullet. There's no, as far as I know, a uniform theory where everything fits. I'm just giving kind of highlights. And we have some ongoing work. So we're doing work on convergent data management and on these confluent systems. And so I thank you. That's it.
We have minutes for a few questions, if there are some. Please.
Thank you for a very nice talk. Very nice. So I agree with what you said, and you had a slide about probabilities, and
yes.
I use probabilities for
probability, yeah.
Modeling our systems, even though it's not really correct.
Exactly.
And then I would say that there's a fourth level here.
Okay.
Because there are three levels, and actually, yeah, here, because we only know the range of behavior,
right.
The frequency limits do not exist. I would say that there are cases where we don't even know the range of behavior.
Oof.
Right, because security is such a thing.
Okay.
We don't even know the behavior of the attacker. We don't know what states we're going to possibly end up in.
Right, so there's even a higher level of uncertainty where, yeah, like you say, the attacker can be much cleverer than us and find out things that we've never heard about, and do approaches that we've never heard about. Yeah, that's terrible.
So how does that affect your design of the system, do you think? Does it, or?
Well, yeah, well, the point here is that don't rely on probability. Rely on the range. So your system has to work for a complete range. So you build here. So you have to assume that there's Dijkstra-Demon in there. So the Dijkstra-Demon in your case is even much smarter than this one. Okay. So how do you build secure systems? Good question. You tell me.
The range is infinite.
The range is basically
range is infinite.
So it's I think you're right. It's a fourth bullet. There are some principles that are known. I'm not an expert in security, although I somehow follow what goes on. But a general approach. I mean, in distributed algorithms, there's these Byzantine algorithms that assume arbitrary cleverness up to a certain degree, but they don't assume social engineering or something like that.
It's even stronger, right? Because arbitrary can be anything. It could be clever, it could be dumb, it could be whatever, right?
Yeah.
Arbitrary is undefined by definition.
Right.
In this case. So, are there more questions?
If I may add here a single thing. So, by the way, thank you for the nice talk. I don't think there is any large system that is Byzantine for error. I don't know of any, so I don't think the answer, how do you build it, I don't think you do. Or we don't know how to
Can
get it.
blockchain be considered Byzantine? It's kind of a cryptographic consensus.
Yeah, but it's a range of behavior because it's not Byzantine for everything. So there are attacks that you can destroy Bitcoin. So it's unlikely to happen, but they are.
Probabilities again.
Exactly. So.
Probabilities, they're evil.
There are actually lots of anecdotal examples of probabilities going wrong, right? So, for instance, Skype used that sort of structured DHT to support the indexing of users. What were the odds that lots of nodes would go down? Eventually, Windows did an update, right? And everyone went down at the same time, and they were 2 days down. So there are lots of anecdotal examples.
And it's even kind of expected in hindsight.
Yeah,
so
exactly.
This is like an example of a black
swan.
Yeah.
You should
so
have
this book is actually really nice. If you have to read it. And actually, he gives a name to this fraud. He calls it GIF, the Great Intellectual Fraud. And so, from his point of view, it's monetary instruments like obligation. And basically, there was this big scam where you have a huge machine, and basically you put manure and inside one side, and gold comes out the other side. Okay, gold. This is what they claim, and of course, it didn't work.
Surprise. Are there more questions? So if not, we have a coffee break now for half an hour, so we feel free. Go ahead.
Just a small remark about probability distributions. I completely agree that putting too much trust in them is very dangerous. But in many cases, for example, the one information about Skype or the cases about financial markets collapsing, it's often when the first mistake is to assume that some phenomena are independent where they're not.
Yeah, exactly.
And this is the very case for Skype.
Yeah,
but if they have modeled accurately that everything could possibly fail with one update, and that there was a probability that was substantial, like 5%, then they would have predicted.
So the notion of independence, because there's information channels outside the system, especially between human users. So you have to make a very, very conservative worst case approximation on this.
The other possible observation is that you need a very complete model to use any form of probability, which is very hard to achieve.
The social model of
exactly.
People, who work on dependable system, fault-tolerant system. Usually, this notion of diversity is a key notion that appear again and again, and of course, visual design approaches to prevent that. But it's very costly. The way you build a plane is not the same as the way you build a cloud service.
That's true.
Okay.
So let's go for the break. We can chat with Peter during the break. Let's thank Peter again.